after the second lecture, you will all go to the laboratory for the first session of the lab, and then in the second half, we'll try to finish by 3:15. So you have to come by 2:15. Just take your lunch well before in time so that you will be at 2:15. Okay, so we'll close the second half by 3:15 or let's say 3:30, and then after that we'll have a closing ceremony, small closing ceremony, where your certificates will be distributed for the course. Okay, so please be on time so that we'll finish by 4 p.m. let's say today. So you'll all have the time to move by train or buses wherever you want. Okay, so in the lecture 9, before that we have discussed about the coordinate system, time system, the GPS signal structure, which was the key to understand how the combinations were prepared during processing, the relative positioning, the single differences, double differences, triple differences, what were the error sources, which were the major source of error for exchanged. Okay, so we discussed the error portion yesterday, where we discussed all sources of error and from satellite end to the receiver end, and obviously those errors are individually a portion of research. Those who are doing the research on ionospheric delay, tropospheric delay, multipath estimation, so these are individual topics of research also. So today what we are covering a bit on strategy for measurement techniques using the GPS. How can we go for different ways of collecting data? So we have this two basic positioning system, one code based, another phase based, obviously for sub-centimeter to meter level with the help of P code, and obviously for the mm level and sub-millimeter level we have to move for phase based. So obviously these were the two fundamental backbone of the GPS positioning. That's how we can claim that we have the mm level position in our so-called points. So we all have understood the mathematical model also for code based as well as for phase based. So code based positioning, in just starting with this for the today's lecture, is that it has a primary application in the real-time navigation system, where we don't want major accuracies when we move from one place to a second place just for the sake of navigation. So obviously the plus minus 0.5 to 5 meter are tolerable. Nowadays handheld receiver are capable of giving 3 to 5 meter in real time also, and nowadays we have a handheld device. Some of you have also seen it, Zuno 3B. It has capability of taking the data correction from the SBAS. The full form of SBAS, we call it satellite based augmentation system. So these are the additional satellites which are in the orbit, geostationary orbits, which provides corrections, and that's why we call it augmentation system. It augments the ongoing satellite navigation system, which we have GPS, GLONASS, Galileo, IRNSS. We have Gagan also for Indian continent. So yes, we can achieve this much with the help of code based positioning because of the availability of DGPS, real-time corrections, which are available from so many sources. You can go for triple P, but that will be phase based. Okay, so two types: single point positioning, differential positioning. We have discussed the mathematical model of single point positioning also in the last few classes. We have discussed the DGPS also, but primarily for which we know the DGPS is for code pseudo ranges, corrections to the code pseudo ranges at the rover position. So the single point positioning achieved by intersecting the measurement from 4 or more satellite. Obviously 4 satellite is for the unique solution, and in order to make your system more redundant, you take more measurements from the satellite which are coming from horizon to a particular place in the space. So using an inexpensive, that's why we are saying that this much accuracy, 3 to 5 meter in general, is possible using inexpensive handheld receiver. Nowadays Professor Herring was talking about that in future you will have a mobile devices which are capable of giving you centimeter kind of positioning, just some after 5 years or 7 years or so. Okay, so this is code based. So obviously this word, the differential positioning, which we understood that okay, DGPS means differential. We have to make sure that our baseline is well within that limit, so that the corrections which we are applying at the rover station, the so-called the relevant kind of precision could be there in the position estimate of the rover. If we go beyond that limit of baseline, obviously we don't consider that further order term in those ionospheric terms, so we cannot make sure that those estimates of the position of the rover are true or not, or good or not. So the significantly reduces, not removes, reduces errors affecting single point positioning through relative positioning mode. So as I said, in literature you will see that relative and differential, they are used interchangeably, but in general we used relative word for phase based and differential DGPS when we say, someone says we have done the DGPS survey, although he doesn't know about the DGPS, although he's saying that we have done DGPS, he majorly talking about the corrections to the code pseudo ranges at the rover. Okay, so most simple form of relative positioning, which can be conducted by applying correction to the code measurement or the pseudo ranges at a sensed at a known monitor site or the base station, which we call it, and to the measurement at the unknown rover site. So using either simpler, cheaper post mission, you can collect data at both rover and base, and you come to your office and you do it in post processing manner. You can also have a real-time processing data link, which can send you the corrections to the rover, whether it's in a radio modem link, or you have now network providers are there. You can use SIM also in your so-called devices, and you can access the correction. But there are a lot of settings which you need to take care of. So real-time DGPS somewhat limited to near line of sight. So what we have done when we have done the experiment or on the DGPS, what we the industry people, they come for the training purpose, so they have shown us the picture where the radio modem at the base station is on the rooftop they have established, so that the line of sight would be clear to the rover stations. Okay, so sub-meter positioning up to 300 kilometer or maybe less than so. This is the for the conditions which are favorable to DGPS. So real-time DGPS is nothing but the corrections which you are providing in a certain format to particular rover. So one popular format which we call it RTCM, which provides the corrections in to the rover site. So yes, it messes types of difference GPS consist of reference station parameter. It takes the correction for pseudo range corrections, because it considers position fixed and it try to measure how much pseudo range are deviating from that true geometric range, and it try to estimate those, as well as range rate corrections are also estimated. So these three are sent to the rover for particular correction at the rover end, but the latency is there, so that you are computing these corrections at t, but you are applying at t naught and you are applying at t. So this t minus t naught is also a term which is there in the case of DGPS. You should take care of these. So several equations are also there. You could also go through some books also. Those who are looking at the position estimate at rover end, what is PRC, what is RRC, pseudo range correction, range rate corrections, you can estimate those and you can try to see how those equations are working. Okay, so real-time DGPS is one of the most popular the so-called mode of surveying nowadays, where you have a reference station, and this was developed primarily because you have selective availability was there at post pre-2000, maybe in January 2000, post January 2000. So you have selective availability available, which degrades the ephemeris and clock parameters from the satellite. It's an intentional degradation of these parameters. So that's why you need to avoid those errors because of these two. And we have seen that if you have certain errors at the satellite clock end, you are prone to have around 10 to 15 meters of error in your range estimates. Okay, so at reference station, it is at known point. So the corrections which are estimated at the known position or the receiver, the base station tracks all satellite in view, compute corrections for each satellite, provide correction in this format, and at the rover station, receiver rover units receives the correction if you are working in a real time kind of something. If you are working in post processing, you don't need to do anything. You just collect your data set, come to your office, do the post processing, simple base and rover baseline formation. Okay, so summary of code based is that single point positioning, whether it is static or kinematic, minimum receivers you need only one, born in static mode, observation time 1 to 10 seconds for a handheld receiver, let's say, and you will have this much kind of the so-called position in say 100 meter horizontally, 150 centimeter. Just a term to understand that it is one of the lowest cost single point positioning. And you have a differential, so you could see the improvement in terms of horizontal and vertical, and need at least 4 satellites. So common satellite would be there, so that correction could be applied in a proper sense. Apply corrections measured at receiver reference to rover. Okay, so another one which we discussed is the carrier based positioning techniques provide a lot more accurate range resolution rate because of the short wavelength, 19 centimeter and 24 centimeter. You have seen the thumb rule is that 1% of that the wavelength could be achieved as in terms of precision. So 2 mm, we are talking about 2 mm. So ability to receiver to resolve the carrier phase at this much level. So several carrier based methods such as which are because these methods are developed so that you can move either in a static sense or in a kinematic sense, so that your the accuracy in your estimate should improve whether you choose from one mode to another mode. Okay, so obviously the static one is most preferred one, most accurate one, which we are doing for crystal monitoring deformation, which we are doing the data set which we are processing in GAMIT, is that these all are static receivers. They collect throughout 24 hour data, and you use those RINEX files for processing. Then another are some deviation from those static. We call it rapid static, we call it kinematic, we call it stop and go kinematic, pseudo kinematic, RTK, or on the fly kinematic. So what they are basically doing in a general sense, when you move from static to another mode, which we call it kinematic, that the mode is generally used for a particular application. So if you are doing the vehicular navigation, you need to go on a kinematic mode. What are the prime requirement for those modes when you change from static? What are the prime requirement? You should also understand that because of these requirement, it is possible to have this much kinematic application. Otherwise, you have to be always in a static mode. Okay, so practical GPS survey technique, we actually follow the static survey. So receiver must resolve phase ambiguity with each occupation, and sessions are longer. So traditional static, rapid static, reoccupation when we reoccupy your station. So we'll see that pseudo kinematic and pseudo static kind of word in terms of the static survey. Then we have a kinematic surveys, which we also called a dynamic. The word dynamic is here as the written is, and if you try to understand those on those models or the parameter in those models which are acting as a force to move that motion. So if you are just understanding the velocity, it's simply kinematic. But if you are understanding the forces acting over that particular object to move it, that moment you call it dynamic kind of something surveys. So these surveys have short duration, not more than 10 minutes, 15 minutes. At each occupation, at these resolve ambiguity once at the beginning of session. So they use the so-called, they have a base receiver with them, and the rover is moving. So they always have this combination, and also loss of lock is not a situation. You cannot move, you cannot think of losing the lock. You have to always be in the lock should be there at always during this surveying. And obviously lock on the satellite maintains that solution for rest of the work. So we call it another certain stop and go, traditional kinematic, on the fly, OTF, real time kinematic. So these are the word when you apply correction in real time in the relative sense. So the mode we call it real time kinematic, similar to DGPS when you are providing the corrections in real time. So static survey, classical technique. Obviously the session length is longer. You could consider that also. So each line is observed for at least 1 hour. Requires more than one receiver, 4 or more satellite, and obstructed sky. Long observation time. For more, the observation session length also varies how much satellite, how good your satellite geometry is, and we have discussed that in the previous classes also. So long observation time, 1 hour or more, in order to remove ambiguities depends on receiver, accuracy requirement, satellite geometry, length of the line. Obviously, you could see that if the baseline length is increasing, you are working in, when with the case of GAMIT session, you are working on a baseline length which is more than 1000 kilometers. So obviously you are working on a 24 hours of data, isn't it? So that's how your deviations for the length of observation session also varies. Okay, so the only solutions for larger areas, accuracy. So these how it varies, 1 ppm for 1 kilometer kind of baseline. Nowadays receivers are available which are giving as 0.5 ppm kind of something. So as baseline increases. So this is how you are working when when you have working in the dual frequency receiver. So if you go through the manual, some of you may not have gone through the manuals, but if you see the manual, you could see the horizontal precision, what they are doing. So it's saying that 3 mm plus minus 0.1 ppm. So the parts per million is actually related with the baseline length. So you could see that this is a very nice figure by the book called Sickle, is that this for 1 kilometer, you could see that for if you have 8 satellite in your view, you could have less than maybe 30 minutes kind of data set, because your satellite length is baseline length is decreased, as well as you have more favorable satellite geometry in space. However, if you go for, you could see the baseline length is increasing, that's how the deviation towards the more observation length is there. So that's why if the more if you are working on a plane area, which you consider as a plane, where baseline length you can consider Kanpur and Allahabad region. So these in those places you can consider that a 1 hour data with 7 to 8 kind of satellites, common satellites, you could achieve those precision which you are thinking about. So generally for geodetic control over large areas, national and continental networks, this is the work which we are doing in GAMIT session, isn't it? Monitoring tectonic movement, network adjustment for higher accuracy, and obviously photogrammetric control, because we want that higher estimation of the dam which we are preparing from the close range photogrammetry, aerial photogrammetry. So we need that control on the ground. Okay, so another version of the rapid static. It is also, as I said, rapid static version is the mode where you achieve highest possible accuracy, isn't it? So the rapid static, which someone call as fast static, is that how you occupy stations, isn't it? And obviously the quality of the receiver is also of another grade. You cannot do with single frequency receiver this rapid static kind of survey. You have to have this rapid static survey with the dual frequency kind of estimate, because they are also using data combinations, preparing wide lane, narrow lane combination kind of something, so that the observables get prepared for well before in time, and the measure short baseline up to 15 kilometer, determine position in centimeter level with short observation time 5 to 20 minutes. Observation time is dependent on obviously these two are the major factor. How favorable is satellite geometry, how favorable, which we call it PDOP. So yes, this is a slight deviation from that pseudo kinematic. We could say that no continuous lock is required with moving rover from one station to the next, since the baseline is processed independently. So what we are doing, we are moving, so we are occupying the station and we are moving, and the need of lock is not required in this case. A combination of, we call it stop and go kinematic, pseudo kinematic, static surveying methods, but yes, the quality of the receiver should be of higher grade. Okay, so in the next is similar to static. You could see that the deviation from the static, here in the static case we have 3 mm, 2 mm, 1 mm, however here it is 5 to 10 mm with 1 ppm. So applications are control survey, fast survey, where you need data within a day for let's say for a city or for an area. So in inventories, detailed survey or data inventories, replace traversing by local triangulation. Advantage, easy, quick, efficient, ideal for short range survey, conserve battery power, because no lock is required, you can switch off your receiver and go on another place. This is how it is. This is one simple representation. You are going from one, this is your reference receiver obviously, 1, second position, shift to second, fourth, then fourth to fifth. That's how you are changing, and you are occupying station twice, isn't it? So that's how you perform this survey, and you can reduce your session length also, as well as you can work with a little improved accuracy from the kinematic one. There is another one is pseudo kinematic survey, simple to standard kinematic, where you have a base, you have a rover, and after initialization the ambiguity is resolved, you can move, so the lock is maintained in this case. So you have to be very careful about on which path you are moving with your rover, so that the lock cannot be lost. You don't have a obstructed kind of sky, isn't it? Sky should be clear. So these kind of surveys are performed with this limitation. No static initialization, longer period of time at each point, typical 1 to 10 minutes. Each point must be revisited after about at least hour, more than 4 hours. Number of satellite does not play essential part. Loss of satellite lock is acceptable. We are actually occupying the second point again in the future. So positional error is more than for kinematic or rapid static, hence less acceptable method for establishing baselines. Obviously, we cannot do this kind of work for the crystal deformation kind of something. Pseudo kinematic, you could see the accuracy ranges are also changing as compared to the static. Photo control, lower order control survey, many mining surveys preferable if points are easily accessible in small areas. You could see that ideal method when conditions are not suitable for rapid static. For example, fewer than less satellites are available, PDOF is weak, PDOF is fluctuating between 5 to 7. It allows for a satellite at second occupation to have configuration different than the first for ambiguity resolution. The kinematic survey, which is allows move rapidly, allow user to move rapidly and accurately measure baseline while moving from point to another. So you have in this set also you have a reference and you have a rover which is moving. Data collected and post-processed to obtain accurate positioning to the centimeter level. A partial lock of satellite is acceptable, but you should not go in the so-called complete loss of lock. OTF technique, which is generally used, which uses the lane combination, wide lane, as well as on the the ambiguity bias solution from the pseudo ranges measurement, and it computes the ambiguity. So OTF is the way. So for occupying two known stations for 2 to 5 minutes, accuracy, you could see the accuracy degraded from that previous rapid static also. It's 10 to 20 mm plus 1 ppm. Observation time, at one point you could have at least 10 to 15 samples kind of something. It's written as 1 to 4 epoch kind of data, but you could have up to 10. Sampling rate 0.5 second, 5 seconds, so that you have enough data set, and then you move on to another point. There's another version which is in the literature. You can see stop and go. There is another method which we call it leapfrog method, where every station changes its position in a sequential manner. So stop mode, before the survey begins, the rover is required to resolve ambiguity. Static initialization on a known point. Go mode, once enough data is collected to resolve the ambiguity, user can now move the receiver to another place. Loss of lock should be maintained for satellite. For kinematic, the loss of lock should be maintained. You should always be in mind that your lock should not be lost. That's how you base station, rover initialized, changes its position, stop and go, take the next position, works. Obviously, the accuracy is a little bit on a slightly lower side. These are generally for the fast surveys you can prefer. So yes, the kinematic OTF survey. So wide lane is at the heart of this OTF. You prepare the lane combination, and some of you have already seen of the EDM measurements where the reflector is there, and from EDM you make certain short and long wavelengths to measure that precisely the so-called decimal point kind of range estimation. So with that understanding also, the lanes are prepared to resolve that ambiguity in a faster sense. So for the carrier phase, on the fly mode is the heart of this process. P-code pseudo range provide for wide lane based integer bias solution. Your battery is low. Your battery is low. Wait, what is it? So you okay. So as I was saying that P-code pseudo ranges provide the wide lane based integer bias solution, which is used in turn to resolve the ambiguity, and differs from rapid statics since P-code pseudo ranges are electrically refined using Kalman filter, and this process allows fast ambiguity resolution to that kinematic modes to happen quickly. Okay, so this is RTK, which is nowadays used also for the so-called the high precision work, where the the base station transmits corrections to the rover. So although the word kinematic is in the sense is not that sometimes you can move your receiver, but generally the RTK word is given for the rover position is at the static mode, and you are transmitting links for the corrections in a real-time manner for the carrier phase solution. So the base station actually transmit correction to the rover using radio link. No post-processing is required. Nowadays, the Trimble receiver which we are using in our labs, we have a PPK mode and RTK mode. So when you select RTK mode, and if you move in an area, then you have a better representation of the points you have collected in a kinematic sense. So the same could be applied into the monitoring of for higher precision work using the RTK. So in the real-time kinematic sense, the same constellation of satellite is available for both rover and receiver, and that's how you placed your transmitting antenna higher so that it has no obstruction while transmitting the signal. You can use Wi-Fi also. Nowadays it is configuration is available if you are using GSM, if you could, but the problem is facing with the so-called with the network provider is that when you use the Wi-Fi as the provider for the corrections, you cannot, if you are using two different network providers, obviously you have to have a setup at your some place which is actually getting the data from the base and transmitting to you. Network providers are not directly sending the data, which we are facing certain problems during previous surveys. So yes, wireless servers which are available at some places, you can use those if both rover and receiver have that access to the wireless. So then you can directly have access to the data set, and RTK is possible. So this is general summary. Baseline length based, you could see that in a static case, however in the rapid static or reoccupation, the baseline length is not increasing. So that's why, because you are working with the base rover combination. However, in the static case, your baseline length could go up to 1000 km, which we are working. And similar to see that in a static case, this is the general accuracy requirement 5 mm plus 1 ppm. Observation time also, you could see that for more than 100 km you have at least minimum 4-hour kind of observation. The session length also increases the more we process longer baselines. Recommended recording intervals for SPP, single point positioning, 30 to 60 seconds, 10 to 100 kind of meter kind of accuracy. SPP with phase, you could see that 3 to 5. Static 1 to 4 hours, 5 mm plus 1 ppm. Rapid static 5 minutes. Recording interval of 5 seconds, you could have this much. Reoccupation, you occupy your station again 1 centimeter plus 1 ppm. So that's how based on these different modes, how you choose in your field, you could deviate from the accuracy requirement also. So how much accuracy you require in your observation, that also correlates with how much session length would be there. How that also needs the common satellite geometry to both rover and receiver. This is another one comparison from the SHGet book. It's very good to read that what are the drawbacks. So static is slow. You have to wait for 4 to 10 hours so that you get good enough data, but high accuracy obviously. Kinematic require constant lock. Your lock cannot be missed, but it's fast. Requires some more sophisticated instrument, I would say, for rapid static, because you need dual frequency. For static, we have worked for many long time. We have worked with the Trimble R3, but nowadays it is not coming from the production side. It is L1 receiver only. It's only single frequency receiver. So we have done a static survey using those L1 receiver. But for the rapid static, you need those dual frequency receiver because of the combinations which you are there preparing. Okay, so another section which we are discussing on the modernization of GNSS. Nowadays, if you purchase, let's say we have purchased a base station called NetR9, which has capability of accessing GPS, GLONASS, Galileo, IRNSS, so many constellations which are available from different countries. So as they are developing, your development from the industry side is also progressing to correlate with these development. So nowadays, so most popularly we always follow GPS, because there are a lot of the content which is primarily available to understand the full functioning based on the GPS only. And then now GLONASS, Galileo, Compass, Baidu, quasi-zenith satellite system, Indian region navigation satellite system is there. Obviously, I have written it is in the GNSS, but the IRNSS is not complete GNSS. It only covers the Indian territory. Obviously, the QZSS also, if you could see, so that covers the so-called the Japanese portion more on a navigation. So obviously, yes, GPS, GLONASS, Baidu, they are all it's a global navigation satellite system. So they cover whole Earth. They move, their orbits are placed such that they cover complete Earth. So obviously, if we look in a general summary, if you start from looking at how the GPS developed from the design objective, you understand, and how it progresses. So one of the major I would say that the advantage of having the ending the satellite ability, so that it could the civilians could could access to these receivers with sufficient accuracy. New civil signal are coming, L2C, where the code pseudo range is the codes, civilian codes are available on L2. New signals, the carrier signals is coming on L5, which we call it another segment of L band, and the L1C, you could see. So these are the new civil signal dedicated towards the so-called and the chipping rate is also increased for CA code. You could see that CA code is not, chipping rate is 1.023 megahertz. Nowadays it is available. In future we'll have 10.23 megahertz chipping rate for the CA code also. So yes, the control segment also improves as the more satellites are available in the space. There is a website called GPS World. You can go and explore how the constellation are improving, what are the present constellation of GPS, and there are a lot of material you could see and read. Simply the block period also there. The previous block period are obviously ignored, because in the case of second R, new satellites are coming, and then follow on GPS block third. Although in literature it is said that GPS block 3 would be available by 2013, but I don't know whether it is is it available? Not yet.
The first block 3 might launch this year.
This year. So we have read from the book that it is start from 2013.
Yeah, the basic problem, probably it is a budget issue. The big issue has been that the satellites last so long that there's no need to replace them. And so that's last year, in fact, we did not launch. I was checking, we did not launch any GPS satellites last year. There was no need. And so they don't, and now the plan is that this year they might launch the first of the block 3s.
Okay. Sir, please. So obviously the communication system is also being replaced with network-centric architecture to allow more and frequent and precise satellite commands that will improve accuracy for everyone. So that's how the summary of GPS from advanced, the replenishment, follow on, third. So that's how the improvement in terms of the signal frequency, the carriers, how the carriers were available in the second day, then they improved. The military code is also coming up, but it is purely purpose is to replace in future the PY code. And similarly the third civil signal, the fourth civil signals, which are coming for the pure civilian purpose. In general, you could see the buttons which are available for L1, L2, L1CA, L1PY, L2PY, and in the future how much buttons are increased, you could have access to military, you could not have access to military code, but also it is available as, so you could see that there is no PY written over it. So maybe in future you will see that these buttons may off. So that's how if you see those signals in the frequency domain, how they look like. So those who are interested in from understanding more, they can follow any book on those covering more on the signal structure. So there's a new navigation message will be developed for the case of L2C for the civilian access. So they will developing, which we call it CNAV, isn't it? So that's how the development is going on, so that you have improved navigation message for the codes also dedicated for. The military codes, L5 new signals, as I said, this is near to L1. It's the L1176.45 megahertz. So both L5 codes, the chipping rate is increased for the CA code also, you could see. So that they now have 1010 combination similar to the P code. Now this another satellite constellation which are more popular after the GPS is the GLONASS, but the major difference you could compare, not in terms of the number of satellite, but I would say that you could see that the repeat period of the so-called GLONASS compared to the GPS. So you are looking at the same satellites slightly before next day in the case of GPS, but you have to wait for around 8 days for the next satellite, the same satellite to see after, because of the inclination of this the orbit. Although they are both MEO, medium Earth orbits, but and obviously the signal structure is slightly changed. You have code division multiplex access. Here it is a frequency division multiplex access. So the major is this, the repeat period also, which I observed personally, is that this is slightly different from the GPS case. So they are also coming the new signals on GLONASS K, which includes this CDMA portion, which we call it code division multiple access. Another one is compass. I would try to draw a few figures for you to understand, is that the satellite track these are the tracks which are there because of the I would say that those satellites constellation which are in the GSO, which we call it sun synchronous. So you could see that these some symmetric 8 figure is available and some asymmetric 8 figure is available. So because the QZSS, which will come in the next slide, quasi-zenith satellite system, they have the eccentricity is more in the orbit. So because of which you have slightly asymmetric figure 8, which in this portion Japanese region is covered more compared to this. So when you place geostationary with respect to the Earth equator, you generally point the same region over the Earth, and it travels with respect to the Earth rotation. So always follow a same region. But the moment you change inclination from this equatorial plane to another plane, it will follow this kind of track. So Baidu has certain medium Earth orbit satellite also, as well as GSO satellites also. But in the case of QZSS, you have the GSO satellites which have this kind of trajectory over surface of Earth. So this is mainly because, and the Baidu is more dynamic, I would say, than in terms of orbit constellation. It has certain MEO, certain GSO, and certain geostationary orbits also, pure geostationary orbit with respect to the equatorial plane. So this is more on a dynamic side in terms of if we talk about the Baidu system of the Chinese. This I was talking about the QZSS. You could see that asymmetric figure of the track of satellite on the surface of Earth. So that's just because you could see those the orbits, those who are the so-called the GSO orbits, is that because the inclination is there, as well as the eccentricity in orbit is near to 0 for the case of Baidu. However, it is near 0.075 in the case of QZSS. So that's why this portion is covered more compared to this. And you could follow the Keplerian third law, I guess. That would be more relevant to understand this kind of trajectory. So yes, our Indian satellite system has also certain geostationary as well as GSO. We have also this kind of similar figure, and also the geostationary orbit which is dedicated for the Indian region. So this is the end of modernization of GPS signal. If you follow GPS world, you could have more access to each and every satellite constellation, as well as the interface document by individual satellites navigation system. You could also read more about their constellation, how they are updating it, and so on. Thank you for this.
You told that there is a dynamic system, dynamic and secondary. We're talking about all the forces working on the system.
Yeah, it is something like.
For example, if I take the example of winter, we're talking about the forces which are working like direct forces.
I would say that let's say if a intentional force is exerted on to the
physical force.
Physical force, I would say.
For example, a driving is exerting a physical force on the vehicle. There is a stationary portion.
Will that also, because the parameter which needs to be estimated with the help of GPS, I guess. In those case, if the parameter, yes,
Okay, that is to give a
vehicle of this, yes, obviously. But if the dedicated only you move on to the only the trajectory information of that vehicle, then we call it a kinematic.
Okay. So how do you differentiate between stop and go and rapid static?
Stop and go and rapid static, I would say that in the case of rapid static, it is obviously the quality of the receiver is improved in terms of moving from one place to another. They form the so-called, and I would say that in the case of stop and go, the initialization is there. After initialization only you can move.
But receiver remains to stop.
Yeah, receiver will take a position, take certain.
Rover will remain to stop.
In the case of rapid static,
Will be switched off.
yes,
Movement
the movement, and in the case of stop and go, both receiver will not move. Only rover will move.
in case of rapid static, we also move.
No, both will move.
Both can move.
Both can move.
Okay. So generally, whenever we put a base, let's say their base station,
Yes.
at the rooftop of this building,
Mhm.
and then we do a survey in this campus,
On the rooftop.
rooftop of this building,
Mhm.
and then we do survey, we
Mhm.
get control points in
Mhm.
this campus,
Mhm.
then it will become stop and go, and not the rapid static.
Yes, both can be followed, I think.
Yeah, I think with all these names for these kinematic systems, they sort of evolved with time, and I think to a large degree they've lost a lot of their meaning.
Yeah.
The biggest one originally was that in the first kinematic surveys that were done, you had to maintain lock on the satellite, and if you lost lock, you would have to go back to a previous occupation to reacquire it. And then the idea of using the pseudo range and the phase to be able to resolve the ambiguities without having to maintain lock, that led to all of these. The first one was probably rapid static. I
Yes,
think the
rapid,
first name
yes.
that was used. But then stop and go, as I remember, is a Trimble trademark.
Okay.
And their receivers had a button on them which was stop and go.
Okay.
And then the receiver would say, you'd set it someplace and it would tell you when you could go again. And then the next big evolution was the real-time kinematic.
Yes.
And what that did was it took the data transmitted by radio link and processed it in the rover receiver.
Yeah.
So in real-time kinematic, you knew exactly how good this position was, and the receiver could then tell you definitively you can move. I remember, and actually even while you were moving it, I remember one example, a demonstration of this, where it was done in a parking lot by one of the field representatives selling this equipment, and they placed a nail in there, and they told the receiver this is where the nail was located, and they gave this thing to a person, and they said, go and find the nail, and they walked around, and it had a little arrow. And the thing I remember about it was the sales rep had actually put his shoe on the nail so you couldn't see it. And the person walks up, and literally the little spiky thing is sitting just over the top of his shoe, and he decided it was time to move it before they put it down. And that was the demonstration. But these days, when you have so many satellites in orbit, we were talking about you definitely need at least 4. But now, most of the time, you have 10 to 12
10 to 12.
satellites visible, and that extra redundancy in the data makes this all happen much faster. And they're all basically all kinematic, common filter-based approaches. I think one of those descriptions there was the on-the-fly was the only distinction of on-the-fly was they were doing the processing with a common filter rather than with a weighted squares sort of approach, I think. But again, these tended to all be proprietary terms. And
These are proprietary.
yeah, and these days I think it's all very much just the real-time kinematic.
Yes.
Where you can move around and the receiver tells you how you can do it.
Yes.
Okay.
Okay, sir.
Next lecture.
Please, Professor Onkal.
Actual SHGet processing. Various things we have for evaluating results, which is one of those critical steps to understand what you have, and then visualization, how you go about looking at your results as we go through. So as I said, the guide to these scripts, they're all stored in your ggcom directory, and we recommend you look at this. I haven't done a count recently, but there at least has to be over 100 of these different scripts which have different utilities look at them. So what these do, these are used
by the programs, and they show you the sort of sequence of inputs and outputs that you need. They're very useful when you want to automate tasks. We saw yesterday that we had those 4 years worth of data that we wanted to analyze. And so rather than doing each year by itself, we very quickly wrote a small script that would do a generic year, and then we could apply that in each of the years. And very rapidly, once we debugged the script in the first year, it was very fast to do the years after that. And that's the general thought process that you have when you do these things. There are also utility programs that are out there. And those are stored in KF utils, and there's ones for the GAMIT utils. And those contain the programs, often that are invoked by the scripts, but also many of those programs you can run directly as well. And again, on the KF side, there's the directory called help, actually GG help, and there's a help files for nearly all of the stuff we have. So you can look at the help files to get an idea. Most of the programs, if you type them without arguments, will start giving you the help, but often it's easier just to look at the help directly rather than that way. So again, these are try to be self-documenting, and basically, as I said, invoke, you get the help without giving any arguments. Okay, so some of the GAMIT GLOBK utilities that can help you sort of set things up. There is a shell script called SHGet times. So when you have Rhinex files that someone has sent you, some data files that you've got to dump, and you don't quite know what's in them, this actually tells you the start and stop times of all the Rhinex. If you've been doing campaign survey measurements, for example, and some people were talking about, well, we have these 3 or 4 hour sessions, etc. And we were saying, well, do you process it as a big part of one day, or do you process it specifically for that time? This SHGet times allows you to look at when things start and stop to give you an idea of what actual interview you want to do. We already looked at the SH updates stinfo, station information. This gets you the metadata from the Rhinex headers. Very, very useful. There's a small little utility program called DOY. We were talking about that many things have day of year. Other things have this GPS week and day of week. You might have calendar years. There's another calendar year you often see called modified Julian dates. This small little program takes any one of those sort of inputs and converts it into all the other inputs. And so again, if you just type its name, it'll give you the help how to do it. There's a convert C program. It converts Cartesians to geodetic coordinates. You'll notice that GLOBK outputs Cartesian coordinates. There's actually an option in GLOBK to output geodetic coordinates as well. But if you didn't turn that option on, you can use convert C to take your Cartesian and convert them to geodetic. Or if someone tells you the geodetic coordinates of something, you can convert it back to Cartesian. There is a GeoList program. We actually haven't looked at that. We could have, but it would tell you precise. We should look at that in the afternoon session. It'll tell you for that stack of data all the different stations that are used as a function of time and how much they're used. Cortran and then convert CSN. There's another program which converts coordinates as well. It's for coordinate transformation as you go. CoreCom is a program that allows you to rotate the a priori coordinate files into a different reference frame. And you remember yesterday afternoon, we ran with the standard international reference frame, but then we ran with a Eurasia fixed reference frame, and then with an Indian fixed reference frame. Well, those other APR coordinate files that we used, those were generated just by using CoreCom to take the original global frame and tell it to convert it into the Eurasia fixed frame or the Indian fixed frame. GeoList to CMD allows you to take a list of all the files you have and generates a use site list for use in GLOBK. This is again useful if you have large data sets and you want to work out specific sites that you want to use to sort of minimize that list. Vel to stab is a way to get that list of stabilization sites we want to use based on the quality of the velocity estimates that you already have. And as we talked about before, this SHGenstats, this is the thing that generates the statistics of your time series. What is the process noise models that are appropriate for each station? Which stations look like they are good reference frame stations to be used? And then it also generates all the input files that you need for GLOBK when you want to use those. So there's other things for getting data. These are used in SHGet, SHGamit. There's SHGet Rhinex, which someone definitely ran because we had all the data available for us. And this basically, again, allows you to get data from the international archives just by telling it what day you want and the name of the archive or a list of archives that you wish to try. You might have, someone had asked in the class that there was these data files that ended with D rather than O. And that D designation, you'll notice they're actually very small, and that's called Hatanaka compression. And it's actually a specific compression for Rhinex data. And what it's actually looking at is, since the range to the satellites mostly remain around 20,000 to 24,000 kilometers, each epoch, they don't change that much. So what Hatanaka does is only outputs the bit that changed. It's actually very similar to the way image compression works. Anyway, this SHCRX to RNX allows you to convert from that Hatanaka compression to the Rhinex. If you use SHGet Rhinex, you don't need to do that explicitly. It would happen automatically when that's run. SHGetNav gets the Rhinex files, the broadcast navigation files from the archives. SHGetMet gets any meteorological files if you're interested in atmospheric studies. SHGetIonX gets the ionospheric files. We don't need to use those, and we haven't used them, but those are very useful if you want to do the second-order ionospheric corrections that we were talking about the other day. And when you run the kinematic program track, they're also useful if you have long baselines. GetH files allows you to get the H files from MIT and from SOPAC. We were talking about those GLX files. Then you can get these directly with that script. SHUpdate EOP gets you a new Earth orientation parameters. And again, SHGetOrbits is the shell script that goes off, gets this GPS high precision orbits from the archives and converts them optionally into the MIT format that we use for orbits. And then SP3fit is a way that you can actually convert Cartesian XYZ coordinates of an orbit and fit it to an orbit trajectory using the orbit integrator to see how close that orbit actually is to something that we know the dynamic forces for. And that's automatically, again, used in SHGet orbits. Now, there's lots of other GAMIT GLOBK utilities, and again, we've looked at some of these, but others we have not yet. SH one-way we looked at when we were plotting the phase residuals, and that's very useful to see the quality of the data. We also looked at this SHPlot EL mean, which allows you to compare many days of data to see how the phase residuals are changing with time. CView is an interactive display program that lets you look at the phase residuals in data. You can look at them in the X files, or there's a C file output from the processing, which we normally delete because they're fairly big, but you can look at those with that. We've also looked at SHPlot pos to plot the time series of positions, etc. One thing that actually can be called in that, it's one of the options, we can plot time series histograms. So if you have 20 or 30 stations and you want to know what's the median RMS scatter of the stations I have, what's the distribution look like, this plot histogram will do that for you. TSView is the MATLAB-based time series displaying tool. We were trying to bring the executable version of that up, and that didn't quite work because of a library inconsistency. SHPlotVel we used yesterday. That was the one which displayed the map of India with the velocities in different reference frames on it. There's various other components you can call in here, a lot of different mapping elements. We did not do things like put topography on that plot, but you can put earthquake epicenters on it. It has if you look at the help, it has many, many different options that are out there. VelView, again, we hadn't looked at. This is one of the MATLAB utilities which allows you to view velocity fields interactively. You can actually rotate them into different reference frames in VelView. If you have your time series file set up, you can actually click on a velocity vector and then look at what the time series looks like that would have generated that velocity vector. SHVelHis plots histograms of velocity statistics. This is something that people often do when you have a large network, and you may have a nice region which you think is not deforming, and you're going to use the histogram of the velocity estimates as a measure of what the statistics are. What does the distribution look like? Does it look Gaussian, or is it very skewed? Is there something characteristic about it? So again, a way of analyzing your data to try to understand what it's doing. SHorg to Vel is very, very useful. People have been asking, well, how do we go about estimating a plate, Euler pole? And we can actually do that for our data. We could estimate an Euler pole for the Indian plate in glorg, and then SHorg to vel will extract that information out of the .org file and create velocity files that you can plot with that theoretical motion. It also creates various APR files that you might want to use as well. TScon is a time series analysis program that, again, I briefly mentioned, but it allows you to directly manipulate time series as well to rotate the time series into different reference frames if you wish, and actually redefine coordinate systems. Again, most useful when you have very large solutions that you're looking at. And then velrot is this program which allows you to combine velocity fields from different analyses and compare them. So in theory, we could take the velocity field that we'd estimated in the Eurasia frame, the one we did in the Indian frame, and then velrot we could actually use to compare those two and to work out what the rotation was between them and how well they matched. In that solution, they would match exactly because they're the same solution as we did it. So TScon you can use to define a new reference frame. Again, this is when you do have large volumes of data. For what we've processed so far, this is not so critical. It basically works exactly the same as glorg, but works on a time series rather than on a GLOBK solution. So the idea is that you run glred to generate the time series, and then TScon would allow you to re-rotate that system into a new reference frame to look at. Sometimes that's good for flattening out time series. You have large velocities in one reference frame. For example, the Indian one, we see there's this large eastern motion. If we rotate our time series into the Eurasia, into the Indian reference frame, then they would actually have much lower velocities. So the time series will look very, very flat. And this is fast because it doesn't use the full variance covariance matrix. So that was quick. I knew that was going to be quick. So those are sort of the main highlights of some of the analysis tools that are out there for you to go back and, having generated a set of results, to have a look at the statistics in that. And there's many, many more than those that are out there at the moment. But those are the main ones that you tend to use on a day-to-day basis when you're analyzing data. Okay, so questions? Because we have one more lecture. It wasn't that fast. Okay, so many of those shell scripts we'd actually already seen, so let's see. So I'll let you come to the next one. So the last lecture is going to be about kinematic data processing. This is actually a really long lecture, so you'll be able to read the ends of it, I think, at your leisure. We probably won't get all the way through the whole thing, because it has both not only the theory about what we're doing, but also some results from different analyses that have been performed. So this kinematic processing, we heard the lecture this morning about this, and the way this is implemented in the MIT software is a program called TRACK, and it is it's a post-processing program. So the idea is you collect your data and then you come back and look at it. It does full, we'll talk about how it does the ambiguity resolution, some basic use of its command line, and some of the basic command lines that you use, and some of the tunable parameters in this program as you go across. And again, this will probably be most useful, this whole lecture, later on, when if you decide to start using TRACK to process it. We often use TRACK for doing, even on static occupations, just to see what the quality of the epoch by epoch position estimate is within a day. If something strange happens, and you have an outlier day, and we saw one case of one station, right, where it was off on a day. We looked at the phase residual RMS. It actually didn't look that bad. So one strategy for that day would be now to go back and process that station kinematically to see, did it move or do something strange during the day? Is there some part of the day where there's a massive thunderstorm or something that has corrupted the position? And then maybe we could actually take that data out and recover a good estimate. So that's one way we do it with static. And of course, for earthquakes, when we have surface wave arrivals, we often use it for doing that sort of thing. So it's kinematic data in general is more complicated than the standard static positioning. And that's primarily because in kinematic movement, you are moving the receiver And as you remove it, or the antenna, as you move it around, it's going into environments where there could be sky blockage at various points. There is actually the whole kinematic motion of the antenna and the tracking loops in the receivers that sometimes don't behave well. So in general, this is not quite as turnkey as the GAMIT processing is. As I said, for most of the GAMIT processing, you never actually have to touch anything. Once you've set it up, it'll just keep taking data in and process it every day with no tuning. Track, you do tend to need to look at it for the specific data set that you have. Track is also a Kalman filter, the same as GLOBK is, so it has a smoothing filter in it, and you invoke that with a command called back, and it just says back smooth. And what that does is, even if you have not resolved ambiguities, when you're getting the trajectory out, the ambiguities are at least fixed values. Whereas if you do it in the forward kinematic mode, the parameters evolve and things are changing. So it produces a much better quality solution. We do have a real-time implementation of this code called TrackRT. That's even more complicated to install because of the way it needs the Nokia Qt4 libraries to be able to do the internet protocol communications, which is somewhat dependent on your system. And then you also need to have set up all the casters that were actually casting data so you can read it. It's basically reading a stream off an internet port to get the data. And it's also designed mainly for earthquake work. So it's meant to be static. So the characteristic there is the Kalman filter, as it evolves with time, does not actually change the position of the station. It's always looking at the difference from where it is. And normally that's because when you're static, the difference, you're no more than 10 or 15 millimeters away. And then if you have a big earthquake come through, you might get 20 centimeters away or 30 centimeters away during the seismic waves, but you're very, very close. So it's not designed to let you pick up the receiver and move it 10 kilometers down the road. That's going to fail with this real-time system. And that's by design. And so it's a, so track itself, it works by actually reading all of the data and then processing it as we go through. So really, kinematic processing depends on the separation of sites. You can actually have multiple static base stations in track. I think one of the longest track runs we've ever done was an airplane flight that went across the whole of the US. And so we actually had a base station at one side of the US and another one at the other side of the US. And actually one in the middle because I think it landed. So we could actually keep, when you go very far apart, you have a problem that the satellites that you can see from one receiver to another receiver are different. And so if you get too far away from your base station, you lose mutual visibility and you reduce the number of satellites that go. So, and when you, so we can do that. I must admit, for separations of less than about 10 kilometers, this track kinematic stuff is always pretty simple. You pretty much can run it under defaults, provided the receivers are not sitting underneath trees or something like that, provided the data is reasonably good. 10 to 100 kilometers, often you start then needing to do a little tuning. And that tuning is associated with essentially is how active is the ionosphere on the day that you are processing, and how good is the data collection. One of the surprising things I have found with kinematic data is that the receivers, when they're sampling, say, at 10 hertz, often don't actually record all the data they've collected. And so in the kinematic processing, it looks like there's a gap in the data, but there really isn't. It's just that it never recorded it. And this is particularly problematic if you have an external recorder, like you're spooling the data off to a hard disk, which is often what happens when kinematic receivers are put in aircraft for doing gravity surveys or doing LiDAR surveys, for example, that because of the volumes of data they're collecting, they actually spool the data directly off onto a hard disk. And in that case, there's often a lot of loss. If you're getting data that is on a telemetry link, like a real-time stream, for example, then often there is missing data because the telemetry link just can't keep up with the data volumes. So, so it gets more difficult when you go to 100 kilometers, but generally, again, not too bad. And again, greater than 100 kilometers, we've actually had some fairly good results. The longest stuff we have regularly sort of done is 700 or 800 kilometers. But again, looking at earthquake processes. So there's a subtle point that for any of you who want to do this is, what is the nature of your kinematic site? And for slow-moving sites, And again, many people use track for lots of different things. We have lots of users who put receivers on glaciers. And some people put them on landslides. So in glaciers, depending which part you're on, they can be moving they can move very rapidly, in fact, several, 100 meters per day in some cases. But in other cases, they're moving 10 meters per day, etc. And kinematic processing is certainly one of the ways you can handle that. But you can often also do it in GAMIT with short session processing. And that allows you, when you do it in GAMIT with short session processing, it allows you to feed the results into things like TSView and other kinematic SHPlot, pause, etc. So when you do it that way, you actually get access to a lot of good utility programs you can play around with. So if you do have one of these cases, you might want to think about how to actually do it, whether to do it in track or whether to do it with GAMIT in this sort of kinematic mode. So you can also put in, you notice we gave an a priori coordinate file to GAMIT, and normally we have tectonic rates in the velocities in that. But you can put in rates that are 100 meters per year or something like that, or so where it's moving 2 meters per day. And it'll have that velocity, and what GAMIT will tell you is the average offset from that velocity. And in a fast-moving site, that technique actually works very well if you have a reasonable estimate of the velocity before you start. So when you do it in SHGamut, I was talking to some people about this, there's this -ses info option. And that allows you to specify when the session starts and how long it is. And so it's very easy then to batch up data to process, say, 6 sessions per day, each of 4 hours long. And you just do the 4 successive runs as you go through. You do the first one, and then again, we use this no FTP option typically because once the first segment of the day is done, everything that it needs has been downloaded as you go across. And you sometimes need some min tuning. We also spoke about this short survey sessions that some people have data from. And the min XF is the biggest one that you typically need to change to make sure that SHGamut doesn't think the thing is just too small to be useful. In the autoclean command file, you don't always have to do this, but sometimes there's this option called trim one way you can look at the help for. And again, trim one way has the same notion that you don't want these tiny little short segments of data typically, and you'll throw them away. Because normally, as you saw, we had 25,000 data points typically per station. So throwing away a few hundred data points because it's short doesn't do any damage. But if you only have a couple of thousand data points because you've set a session up that's very short, then that can be quite lethal. And so sometimes if you're throwing away more data than you want to, then the trim one way is the other thing that you can do. So as I said, track also can be used for this. Okay, so the reason kinematic surveys, you might have noticed even in the accuracies in our last lecture, they get worse with distance. And the reason for that is twofold. As you increase the distance, you increase the ionospheric delay difference between the stations, and you also increase the atmospheric delay differences as you go across. Now, the increase in the ionospheric delay itself is in theory not a massive problem because we're doing dual frequency ionospheric correction. So we can get the correction correct easily enough on the long baselines. But where it makes a difference is that when you want to look at the L1, L2 difference in ambiguities. If you remember, we had that the lecture where we talked about those different combinations of data. And one of them is the geometry-free combination, which is where you've removed the geometric part, and what's left is the ionosphere. So on the short baselines, if the ionosphere is assumed to be 0, you know that combination ultimately has to be 0. The difference has to be 0. And so you can calculate the number of ambiguities you need to make that happen. And that's an extremely sensitive test, and it works extremely well, provided the ionospheric delay is not large compared to the size of a cycle of 20 centimeters. And as you see, the total ionospheric delay is typically tens of meters. So it's a big amount, but too close stations, it tends to cancel out. So when you go to the longer baselines, we have to use this Melbourne-Woburn wide lane using the Pseudo range and the phase to be able to resolve that difference. And that's a noisier process. And so the longer they get, it needs to be noisier. And that's because it's a noisy process, the more data you can have, the better. So if you've got gaps in your data because your kinematic receiver's been going underneath trees and things like that, breaking up the sequence, it makes it more difficult. The atmospheric delay, always in general, the further apart you get, it gets a larger difference in the atmospheric delay. And again, if you're doing kinematic survey where there's massive thunderstorms off to one side of you, all the GPS signals coming through those thunderstorms are going to be incredibly delayed by that water vapor that's in those thunderstorms, and that will make your processing much, much more difficult. So as I said, for baselines lengths that's shorter than 2 to 3 kilometers, that basically can be treated exactly as 0. The L1 and L2 get resolved separately, and the positioning can just use the L1 and L2, and that has less noise in it. So as you go to longer baselines, you need to use this Melbourne-Woburn wide lane, as we spoke about, to resolve that difference. And again, these IONIX files, which we haven't looked at, but they're estimates of global maps of the ionospheric delay, those can be included to help resolve it on long baselines. So if you're doing anything more than 300 or 400 kilometers separation, we certainly recommend that you download these files. And again, the help tells you how to do that with these things. So as I said, TRACK uses this Melbourne-Woburn wide lane to resolve the difference between the L1 and the L2 cycles. And then it uses a combinations of techniques to determine the L1 and the L2 cycles separately. It will scan data and add what we call bias flags, exactly the same as we do with the static positioning, at times where it thinks there are cycle slips that have occurred. And then the ambiguity resolution tries to resolve those cycle slips back to integer values. And to do that, it uses LC, which is the linear free combination of the ionospheric delay. That's the geometric part. So as you actually fit the trajectory, it can get an estimate of that as a floating point number, and then it works out whether it can resolve that to integer successfully. The Melbourne-Woburn wide lane, which directly tells you the difference between L1 and L2. And then ionospheric delay constraints that determine, which work very well when the baselines are very short, but starts becoming unreliable as you get much longer than that. And again, it's a Kalman filter smoothing approach, so the non-resolved ambiguities are constant in the final solution, and then also the atmospheric delay estimates in the final solution are consistent with the process noise that you've developed. So the ambiguity resolution, the term that we use there is an algorithm. It's called a relative rank algorithm. And it'll just be sort of RR is the way it's represented. So as it tries to work out whether it can resolve an ambiguity, what it does is it just says, what is the quality of the fit with my best guess of the ambiguity set to a certain pair of integers, relative to what is it when you take the next best guess. So it has a set of measures. So the Melbourne-Woburn wide lane, for example, is an estimate, the number of L1 minus L2 cycles. So you calculate that quantity. The number will come out at some value, and it will have some RMS scatter associated with it. So if you're lucky, it comes out, a number like 99.9. And it might have an RMS, which implies you know that value to 0.1. So you say, oh, that's pretty obvious that it must be 100. And so you're looking at the difference between the value you got and the uncertainty with which you think you have it. And that gets you a chi-squared number for that fit. Well, it does that for the Melbourne-Woburn wide lane, does it for the ionospheric constraint value. How well does it actually match to a 0 value for the ionospheric constraint? And it does it for the LC residuals. How well do the residuals change when I actually take the value from the floating point to an integer number? And it does that calculation for a choice of ambiguities, for a given choice that it's trying to resolve, and it looks at the best and the second best. And then it makes the decision whether the ratio of those two exceeds a certain tolerance. Now, because we don't want to get it wrong, we make that tolerance quite large, and that's one of the tuning parameters, is to say, well, I can be a little more risque, and I will go for a lower tolerance because I trust these algorithms. And that's one of the changes you can make. So the one that's there is designed not to make a mistake. You can lower it and be possibly able to make mistakes as you go across. So it does that, and it looks at that, as I said, this relative rank RR, and it's the chi-squared from the match to the LC combination, the Melbourne-Woburn wide lane, and the ionospheric constraint. Now again, one of the tuning things you can do is you can set the relative weights between these as to how important they are. So again, the Melbourne-Woburn wide lane, if the instrument's working well, generally we keep that at unit weight. But we do have instruments where the pseudo ranges aren't being measured very well. And so we have systematics there. We also talked about differential code biases back in the lectures, one of those files that you need to keep updated if you're working in near real time. So if the pseudo differential code biases are not correct, this Melbourne-Woburn wide lane won't work well. And so you can downweight it if you wish to. The biggest one we end up downweighting is this ionospheric constraint. The longer the baselines are, the less weight we give it, and so as we go across. And this gets all iterated, and it keeps getting iterated until it's either resolved all the ambiguities or a pass comes through where it can't resolve anymore, and then it stops and outputs your results. So the Melbourne-Woburn wide lane, it's, as I said, we talked briefly about this, is the difference between the L1 and the L2 phase, and an estimate of that based on the pseudo range values, and it should be an integer value as we go across. So I'm just going to give you some examples of what this thing looks like. We didn't actually look at this with real data, but it's, in principle, because of the way the system biases are, in a one-way measurement, so it's just a single station to a single satellite, this Melbourne-Woburn wide lane should be constant, but it doesn't necessarily have to equal an integer because there's this sort of unknown initial phase that starts up in the local oscillators. And that's common for a ground station looking at two different satellites. The value for the ground station is common, and for two stations looking at two satellites, it should be all differenced out if everything is okay. So the other interesting thing is when we look at this, there's often slopes in this Melbourne-Woburn wide lane, and again, that has to do with instrumental biases that will actually cancel out when you go to double differences. And so as you go to satellite pairs, it'll actually cancel these things out. So the basic formula for this equation, we saw this earlier actually, it's just the difference between the L1 and the L2 phase minus the difference in the frequencies between L1 over L2 divided by the sum of the frequencies over L1 and L2. And then this is the L1 range expressed as a phase. And the interesting thing in this equation, this is the L2 shown as a phase. What's interesting is you add the pseudo range values together. And it sort of sounds very counterintuitive, right? You've differenced the phase, but somehow you add the ranges together. And that addition of that sign, that has to be related to the fact that the ionospheric delay is opposite signed between the phase and the range. And you can actually take raw data. You can take the Rhinix data files with the phase and the range and compute this number yourself and have a look at it. In fact, that's all this next set of plots is going to show, is exactly that calculation. And it is amazing how well it actually works. The other interesting thing to note here is this is the difference over the sum of the frequencies, and that ratio is 0.124. So that means that the noise in the range is actually reduced by about 10% of its original value. And that's, again, something that makes this sort of work, is that it tends to reduce the size of the range noise. And since it's supposed to be constant, you can average it over a number of range values to try to get the noise down better. Okay, so this is an example of what it looks like. And this, as I said, is directly out of the raw Rhinix files. This is time in hours down the bottom. So this is a period of about 4 hours of data. There's two satellites shown, PRN7, PRN28. And this is actually the number of cycles that we're calculating, 200 million or something like that. But the blue lines that go across, they are 1 cycle apart. And so you'll see that the actual mean value, it does drift, and then one's on one scale, one's on the other scale. And what you'll notice is that there's actually about exactly 1 cycle between those two. And that's what we're doing. We're taking that difference, we're taking differences between these values and averaging it, and then trying to work out what the average number of cycles is between them. Notice also, these satellites are setting. And so as you start setting, you just get much, much more noise in the range. We saw that in the elevation angle dependence, in the phase residuals. You saw it in the multipath range plots yesterday. That's a common characteristic. The lower the elevation, the more noise. So this is more difficult to do when you're down in this part. And that is actually part of the problem with kinematic positioning, is when the satellites are getting low on the horizon, the noise in everything is increasing dramatically. And also, when it's low on the horizon, is the time when you're likely to hit an obstruction. If you're driving along, you're likely to go by a building, and the building will block the sky. And then when it reappears on the other side of the building, the only thing you have left is this really noisy data. So that's what track is doing, is it's looking at that stuff, and some of these little noisy segments of data, it's just going to say, that was just far too short after I reappeared after the building, and I won't be able to use it, and it will throw it away. That's part of the logic. Or it might keep it, but it won't be able to resolve it to an integer ambiguity successfully. The other term you will see used in the output of track is what we call the extra wide lane. And this actually goes by many different names depending on who is doing it. But this was also what was called the geometry-free measurement. So it's the L1 phase minus the L2 phase scaled by the ratio of the wavelengths. And so for any geometric range change, this will actually be 0. Because when you change the distance by 1 meter, you have 1 meter divided by 0.192 cycles of change for the L1, and divided by 0.244, the wavelength of L2. So this is just the ratio of the wavelengths. And again, if the ionospheric delay is very, very tiny, this should be very close to 0. There is a subtlety, and again, when you start looking at track, you will worry about considerably, is that Melbourne-Woburn wide lane, which we believe we can resolve usually quite well if the instrumentation's good, tells you the difference between the L1 and the L2 cycles. So then everything else after that is at 1 change at L1, 1 change at L2, or -1 and -1. And then when you look at this EX wide lane, you'll see that if I change the L1 cycles and the L2 cycles by 1 each, then the difference is going to be 0.28 cycles at L1. That's the equivalent of only about 53 millimeters. So this 53 millimeters, you get ionospheric correction of about 82 millimeters from a half-tech unit of ionospheric delay. And so if there's a differential half a tech unit, then this is going to start getting confusing and be difficult to resolve out. And that's when you rely on the LC combination to be able to resolve it as you go across. But on short baselines, that works really well. So it's, again, as you go to longer baselines, as you go. So what do you have to give to track? Track is like GLOBK, runs on a command file. It's a command file that, actually, as I think about it, we don't actually give any templates for, simply because it's the basic elements are always the same, but the names of things are very, very different all the way through. You might have noticed in the GLOBK templates, we didn't actually need to change very much, right? And that's because all of the files we were referring to were standard files down at the, someone's got a phone call. So anyway, but when you run track, the big ones you have to do is a command called obs file. And that's where you name the Rhinex files that you want to process. And it runs directly off Rhinex. And then they're designated either as K for kinematic or F for fixed. We recommend, actually you should only have one fixed site. And if you have another base station, you treat it as kinematic, but you give it 0 process noise, so it can't move. And that's the better way to do that. So you have to tell it that. Then you have to give it a nav file, which is either an SP3 orbit file, if you have it available, or a broadcast ephemeris file, if that's all you have available. If you're doing anything post-processing, we certainly recommend that you get the SP3 files when you do this. And then what we normally do is there's actually 3 sort of modes that it defaults in. And there's mode air, which is appropriate if you're using aircraft data, fast-moving, long-distance stuff. Short, which is appropriate if you're using really short baselines, less than a couple of kilometers. And then long, which would be appropriate if you were doing long-distance stuff, anything more than a few kilometers. And then normally back type smooth would normally be specified. This is normally where you start. You run that solution, and you look at the output that comes out of it. There will be a summary of what the ambiguity will look like. It will automatically output your time series results under default names. And if it looks good, quit while you're ahead and go on to the next day of data. So hopefully you don't need to tune. But then when you look at that, that's when you have to start doing the tuning process. And that's where all the skill is in doing it. So what's going to come out of this? Generally, when we run track, we again pipe the output into an output file. So the thing you look at is, remember grep is this thing that we really like to use to grep on things. So you look at two types of lines, the ones which have PRMS, which is phase RMS, and then the other one is a type from the summary file that's written out, which by default would just be track.sum if you didn't actually give anything. All the units here are in millimeters. And in this particular case, what it's showing is that this site, UNSC, has a 7 millimeter RMS scatter. This site has a 7.2 millimeter RMS scatter. This one has 7.4 millimeters RMS scatter. And then this is actually by satellite as you go across. And you'll see we have 1, 2, 3, 4, 5, 6, 7, 8 satellites. This is about 1 hour of data, as I remember. So that's exactly what you want. You see lots of 7.2 millimeters. That looks good. So check one, not a big problem yet. And then on the output that came out, you check the word kinematic, and that's going to basically tell you the kinematic nature of the site that you had. So it says basically that this USNN3 had RMS coordinates of about 1.2 meters or so, and it appears to be static. The coordinates, a priori coordinate, and it tells you how far away it differs and appears to be static. This site also appears to be static, and this one called Rover has RMS scatters of 17 or 18 millimeters and appears to be dynamic. So the next thing you check is that your site that was actually moving does actually appear to be dynamic, and any sites that we're using as a base station as supposed to be fixed, that they actually appear static. And again, this looks really good. And this message, the reason for this head here is this message actually gets reported multiple times throughout the output as you go across. So if your behaviors look good, then you're a happy camper at that stage. And so we'll come in and look at a little bit later on some of the other outputs that come out. But to run track, the general command file is here, is track -f, and then the name of the command file, that is required. And then you can actually tell track values for the ambiguities themselves and have them applied. Now, the way you normally use that is you actually run track, it outputs the ambiguities that it has, and it tells you whether it was able to resolve them to integers or not. And so what often people will do is they will look at that, and as I said, that decision it automatically makes whether the relative rank is good enough. And someone might decide, well, it said the relative rank wasn't good enough, but I think it is good. So you can take that ambiguity file and you can change the status of an ambiguity from being not fixed to being fixed. And then you can take that file, feed it back into track, and run the solution again now with those ambiguities being fixed. When we do really long baselines for earthquake cases, where the sites are static at the beginning, and we know their coordinates typically very well. They will have a period of seismic wave arrivals. In many cases, then after that, they're static again. Well, we can tell track that there's a dynamic period in which there is going to be kinematic motion of the stations, but it's static before and after. So we'll run track telling it that and resolve the ambiguities, and then take that ambiguity file, go back, rerun track with that fixed, but we now say, okay, it can move all the time. And the advantage of that is that the moving all the time period then when it's static lets you get a measure of how much noise and fluctuation is in your static so that you can interpret the quality with which you can determine the seismic wave arrivals. So this ambiguity file, that's a very typical way that we actually generate it. There's ways that this command file, if you remember when we did GLOBK, we had the option of putting things at the beginnings of the lines which would allow them to be replaced. Well, track has a similar feature, which you can give it -d, and then it's going to be typically a day of year. So it's basically referencing the Rhinex file, day of year. And then inside the file, the command file, you have a string, day, and it gets replaced with whatever you put in here. Normally, it is the day of year for the Rhinex files. Sometimes we'll also have there's a -week entry, which would allow you to reference the SP3 files, for example, by week that you're using for the orbits. And then it has a generic set of optional strings, which you just give different values for. And again, these get replaced. We use this to do file naming inside. And so we can also, one special case in here is you can make this the word space, S-P-A-C-E, and it will replace that string inside the command file with a space, which if you remember the way the commands work, where any non-blank character, a space character in the first column is a command, it's a way to have something be a command in some cases, but not be a command in other cases. And so again, it gives you a lot of flexibility if you think about how you want to actually set up your solution as you go across. So when you are checking things, the things to check is to grep final in the summary file, and what that will tell you is the final set of ambiguities it had, and whether they were fixed or not. There's a column 3 which has fixed as its label, and if it has 1 in it, it means that it's still a floating point estimate. If it has 7 in it, it means that it was actually fixed. It's strictly, actually, it's a bit mapped. It's a bit mapped word that you can set the octal code for, essentially. So if it's still non-fixed, biases and the atmospheric delays are estimated, it's good to do that. You can output in various forms. We can output in northeast up, which is sort of a measure of distance, and it's the distance northeast and up from the base station that you were using, calculated in converting geodetic lats and longs into distances, calculating using the latitude of the base station. So it's a useful way of getting a good sort of graphical way you can plot something in meters. You can also output in geodetic latitude, longitude, and ellipsoidal height. That's really good when you're doing aircraft. You can take those files, and we have a shell script that allows you to convert them to KML, and then you can show them in Google Earth. So if you've done an aircraft flight, you can actually show it as the trajectory plotted onto Google Earth, which is sometimes useful. Or if you've done a survey around, your building survey, for example, if you enter in the building, you can actually display it back on Google Earth. Hopefully your Google Earth registration is good. Sometimes, actually, in fact, the option when you do that is actually to allow it to shift it a little, to line it in case you're... Google Earth is actually quite good in Boston. We don't normally need to shift them. But in other places in the world, we've noticed that the imagery is not really lined up with geodetic lat and long in quite the way you might think. There's also a DHU option, which is difference in horizontal and U. It's again a northeast up sort of thing, but it's now in millimeters and it's relative to the initial starting point of the kinematic site. And that's what we use for earthquakes and things like that, where we have a static site and then we know its coordinates very well, and then it has seismic wave arrivals. It's just a nice convenient plot to do that. You can output them in Cartesian XYZ. Some people like to do that because they want to do their own UTM transformation or whatever on the results. There's so many possible ways you might geographically display this stuff that this is a useful output for doing that as we go across. So there's some more advanced features in Track. It actually has a large help file, very large, and all that help file also contains strategies for using the program, etc. And it's, and again, that's what you have to sort of work your way through as you play around and try to understand what your solutions are saying. As I was saying before, it's possible to read in the Track ambiguity file, and what you do is you look at the, grep those final lines, and if you want to switch an ambiguity from being free to being fixed, you change the column from 1 to 7. And 7 is actually 3 bits turned on, and that's really what's going on. The bit 0 is that the ambiguity exists, then bit 1 if it's still free, and then the third bit, which is what you get with 7, is the thing which actually converts it to being an ambiguity fixed as you go across. So some of the advanced features, the thing that people tend to use, as I said, there's lots and lots of options you can do out here. The biggest things people end up changing are the ionospheric constraints that are used and the weights for the Melbourne-Woburn wide lane. There is actually an explicit ability to delete data out. We've certainly had cases of kinematic receivers that one of the satellites just, for some reason, is just very, very poor quality, and we just delete it out completely. Sometimes it's not in the ephemeris, which can be an issue. Some satellites can be tracked by a receiver, but in the global network, not enough receivers are tracking them to get a good orbit on those satellites, and they don't actually appear in the SP3 files. And you can explicitly add and remove the bias flags. That's sometimes useful if the automatic algorithms are either missing something or they have added too many bias flags because there are little gaps in the data, for example, that aren't needed. Okay, so we're at about noon right now, and you want to do a lab session, right, Beef? Yeah. So as I said, this is a really long lecture, which I think you can read at your leisure as you go through. But the rest of the lecture, I'll just sort of whip through it really fast to show you what's in it to give you a sense. But what it's going to talk about is the tunable parameters and the things that you might want to change, how you go about setting up how to resolve ambiguities, etc. As I said, you can add and remove user and bias commands. And then there's the track output files. So again, there's a summary file, which you can name explicitly if you wish, but it defaults to track.sum. The position files, they have these characters in their names to show you what they are. You can output the phase residuals if you want to do more analysis of them. You can also put the wide lane values that are being calculated. You can put them in a file, so if something really strange is happening, you can actually look at those and see why it missed a cycle slip, or why it appeared to put one in that you didn't think it should have put one in. And again, all the meanings of what's in these files are described in the help file. So the summary file, again, basically just gives you a summary of what was done, the residuals, etc., and the options that you used. The track output tells you lots of different things about the estimated parameters, whether you've got what it thinks are bad data, etc. in there. It tells you things about the bias flags and the Melbourne-Woburn estimates that were given, etc. And again, continues lots of different outputs out there. This is probably one thing which you definitely want to look at. Again, one of the problems we always have with these presentations is these lines are long and they tend to wrap. But the way that we designate whether an ambiguity can be resolved or not. This is an example where two ambiguities are not resolved, and the column here called relative rank, that's what it's saying. So the first one, this relative rank, is 2.36. So there's not much difference between the best two. That is something that we just would have as relative rank as the F code as to why it was not resolved, and it's just too small. That's fairly clear. The next one, the relative rank, is almost 10,000. It looks really impressive, so why wasn't it resolved? Well, the reason is S in this column, and S means that the floating point sigma estimates are too large. And if you go back over to the column, here is the estimate of the ambiguity. It's minus 0.16 plus or minus 0.7. And that does look like it's way too large. But the thing that track does is it actually has a correlated noise model inside it. We've seen already, we see correlated noise everywhere. And when you have high rate kinematic data at 1 hertz, if you're assuming one white noise, your uncertainties drop dramatically fast, and we know that's not valid. So it has a built-in correlation constant in it, and that is, again, meant to be conservative. And so we often end up with these sigmas being larger than they probably realistically are. And so one of the ways we do that is we just simply make the tolerance on the sigmas be larger to numbers that you might not think make sense, but actually work quite well. So you could go back and change the tolerance on the sigmas to have this happen. And so it's saying that if I did that, this would get resolved on the sigma. The other column here, the O, is actually a little more problematic at this point. The O means that this is a double difference to ambiguity. It can be resolved, but one of the other one-ways in that double difference has not yet been resolved to an integer ambiguity. And so there's going to be an iterative process. And so hopefully later on in this output, it will come out and that other one will get resolved, and then this one will come back and you'll be able to fix it. So as you watch it evolve as it resolves ambiguities, as they resolve, it allows other ambiguities to be resolved as it goes through. And again, that's the strategies for improving the ambiguity resolution. There's also this ionospheric constraint, ionospheric model you can get in from the FTP at CDDIS, and we go to that. Uses the ambiguity files. So the other tunable parameters that are out there, again, reasonable discussions about how you should go about doing that. Plotting the results, there is an SHPlot track, which allows you to plot those different DH files, etc. You can also, we showed this yesterday, there's a little X Windows graphics package in GAMIT or in GLOBK called CPlotX. interactive, has its own, it's both interactive and batch controlled, has its own help inside, and it has a help on the outside. You can use commercial programs. I use either MATLAB, GMT, and then Kaleidograph is a commercial program that does nice 2D sorts of plots. And then again, all the output files are ASCII, and they have various time tag styles in them to allow you to plot different fashions. So this is just an example of an SHPlot track output, and again, just showing you east, north, up, and then the atmospheric delay estimate that goes with it. And this is the KML. SHKML allows you to convert a track output to KML format. This is an aircraft trajectory that we did for a gravity survey down in Louisiana, as I remember. So if you zoom out, this is a curtain wall on it. It actually shows you the altitude. If I remember correctly, that's the airport. So it takes off from here, flies out, flies around, and comes back again. And then sort of final comments here. The data gap in track is default set to 1. So if there's a missing epoch of data, it assumes that you have run out, that you've got a cycle slip because you lost lock. But as I said, many, many recorders do not record all the data. And as a result, it's often you have gaps and there is no cycle slip in there. So the first thing we typically do change if it looks like reasonable data is we increase the gap size. And there is a parameter, the bfset command that allows you to do that. The sigma limits in the LC are also often increased because we have this correlated noise model that's very conservative, and the sigmas just become larger than they need to be because it assumes everything is so highly correlated. Make sure your antenna and receiver information is correct. If it is mixed, that's the same message we gave in GAMIT. Often with kinematic surveys, I must admit, they work the best when it's the same brand, antenna and receiver at both ends of the line. But you can mix, but then you need to have the correct phase center model for mixed antennas, and you have to have the correct DCB file. You have to put in that DCB.dat file, and you have to tell track what type of tracking it is, which you get from the RCVant file. And then, again, treatment of the atmosphere delay. Again, one of the issues is there's always extremely high correlation between the atmospheric delay estimate and the height. And so often we end up running atmospheric delays as just constant parameters to stop that happening. And there's actually an interesting scenario of atmospheric delay treatments in track, which are associated with aircraft. So you have the ability to have an atmospheric delay which is loose while the aircraft is rapidly rising in altitude. And then when it settles in to do its gravity survey and is remaining at about the same height, the constraints tighten back down again based on the rate of change of height. And then when it lands, they loosen up again because the atmosphere is changing so rapidly as the airplane lands. So there's lots of tunables of that type. And again, the weights you use for the EX and the ionospheric delays. So I think that's a really good place to stop because it's just afternoon. Now I believe the rest of this is actually a set of examples. And those are worthwhile just to look through at your leisure. Okay, so that's the quick introduction to track, which we never got to play with at all. And as I said, you might explore it with, as I said, on short baseline stuff. You could look at the local site that's near here that's not your site, the LCK. Yeah, that's how about 20, 30, 40 kilometers away?
From here?
Yeah.
No, it is around 90 kilometers from Kanpur.
From where the other receivers were. So 90 kilometers, that's a good kinematic size. And you will start seeing the impacts of multipath and things like that when you do this. If you do kinematic positioning every day, that same 4-minute shift that you see in the phase residual, you will often see that same 4-minute shift in the position estimates as a function of time. So if you wanted to play around, that's probably a good baseline to play around with initially. Okay, questions? Oh no, that was the end of the slide. Okay, I thought it would. I think I pointed to the other classes we've taught. The one we did in Boulder last year. There's another track presentation after that, which has lots of examples. Yeah. Mm-hmm. Yeah, I think As I said at the beginning of the week, it's like drinking from a fire hydrant, right?